Hello, hello, am I audible?
Hello. Yeah, you are audible.
Okay. Do you have any questions from previous sessions?
No, sir. This is my first session I'm attending.
Okay, I guess we can start. Let's wait for 2 more minutes. Let's see if anyone else will also join. think, okay, let's start the session. Have you tried this week's assignment? Does this question similar to what you had done? Can you please turn off your mic? Okay, so in this question we have been given a lot of details. First thing first, this is a PMOS, right? As we can see from this here, from the description given in the schematic. And then we are given this is the current equation which holds that is the device is in saturation. Okay. And the current flowing through the circuit is 124 microamperes, right? K is given to us as 3.83 millisiemens per volt, and VT, that is the threshold voltage, is zero point 0.5 volts. Okay, what we need to do is we need to find R1, R2, RS, RD, right? These are the four things we have to find, right? So since we are not given values of R1, R2, we cannot directly calculate VG here, right? Here it is VG. This is ground, so this will be total VG. So we need to follow some steps, and we are given this information. One is that the current flowing through this network is zero point 0.5 microamperes. That is one information, and this we know that the total current is 124 through the device. And one more important thing is the gain is given to be minus 5. What does the minus signify here? Negative sign. That is the
If the
phase.
input is a sine wave, then the output will be inverted sine wave.
Yes. Phase change of 180 degrees, right? Okay. So, and one more important information that is given that the output swing. One second. So, output swing, that is if this is my input, my output should also have a swing, complete swing. One second. As if this is my input, my output should also have complete cycle, right? There should be no distortion. There should be no, for example, this limitation in your device. That is a maximum swing. So with this information, we'll start. First, let's see the current to R1 and R2 is zero point 0.5 microampere, right? That means there's a voltage of 5 volts here. If I directly write the KVL, that means this is VDD. Let's call this as VDD. VDD will be equivalent to the current through this network. Let's call it IN R1 plus R2. That is the total resistance through the network. Because in MOSFETs, we consider this current to be, for the analysis purpose, to be zero. So So that means VDD, that is 5 volts, will be 0.5 microampere multiplied by R1 plus R2. So basically, my R1 plus R2 will be equivalent to 5 by 0.5 mega ohms, right? Or 10 mega ohms. This is one information we need it later. Let's denote it as one. Okay. Another thing we can calculate is also ID is given to us as 124 microampere, right? It's given in the question, right? And for the device, the current equation is K times VSG minus VT whole square. So I can write 124 micro K times VSG minus VT whole square. So that means my VSG minus VT will be equivalent to 124 micro, where the K is equivalent to 3.83 millisiemens per volt. Let me just write here. Okay. So this will give me the value of VSG minus VT, that is equivalent to square root of 0.124 milli divided by 3.83. That comes out to be 0.179, and the unit is volt. This is another information I got here from this equation. Okay, let's keep it as it is for now. Okay, then another information given to us is gain. Do you know how to calculate gain in the circuits? For example, if this is your circuit, how we can calculate the gain? When we say gain, it's a small signal gain, right? So what is the first step? First step.
minus VMRD.
First step is to draw an equivalent circuit, right? Okay, I will draw equivalent circuit. If I'm somewhere wrong, please do correct, right? That, for example, for small signal analysis, we always consider these capacitors to be shorted. So that means this is my V in, and DC operating biases, DC biases are considered as ground, right? Or if they are in between the two branches, they are considered short. This will be resistance R1 parallel, R2. This will be my gate bias. This is source, and here, if you see, this one is the source, right? This one is the drain. So source is the resistance of RS, okay, and this will be equivalent to GM VSG, and this is the output resistance, that is RD, and this is V out. Now can you calculate what is V out? What is V out here? Current is coming from this direction. V out will be simply equivalent to this GM VSG. GM VSG is a current, and I have to multiply it to the resistance, that is RD, right? So this is my V out. My V out in simple terms now will be GM RD, and what is VSG? That is simply VS minus VG. And here, if you see, this is at a potential of Vn, that means this is at a potential of Vn, that means Vg is at a potential of Vin, right? So my V out is simply equivalent to GMRD Vs minus Vin. Now we have another unknown here, that is Vs, right? So we need to calculate Vs as well. So what will be the next step to calculate Vs? If I see here at this node, to calculate Vs, we will do a KCL at this node as well, right? Okay, KCL at this node as node S. So it will be basically, if I just draw the current here, let's say current comes, whenever you do the KCL, you have to find, if you give any current direction, yes, you have to follow the properly the Kirchhoff's rule, right? So if I give a direction here, let's say like this, and this current goes like this, so I can directly write Vs by Rs, right? And if this current both goes away from the node, then this is equivalent to Gm Vsg is equivalent to 0, right? This is correct, right? So my Vs is equivalent to minus Gm Rs Vsg. Stop me here if you don't understand it, please. So my Vs will be minus Gm Rs, and this is simply Vs minus, and Vg we know is V in, so I can write V in. Now we see here, this is Vs here, Vs here. When you take it towards the LHS, that will be Gm Rs Vs, and this will be simply equivalent to Gm Rs V in, right? So taking Vs common here, so Vs I will take common, that will be 1 plus Gm Rs is equivalent to Gm Rs V. Always just remember one thing. If you want to see if you are doing correctly, you can check the units here. Since one is a unitless quantity, right? One is unitless. So if you want to see if your steps are correct or not, you can see that your this term should also be unitless because one is unitless. They should have the same unit if they have to be added. You can see that Gm is always a reciprocal of R. That means this is ohm inverse, this is ohm, this will go. Therefore, that is also this term is also unitless quantity. So this is correct, right? So this is one way to cross check your equations. So that means my Vs will be equivalent to GMRS Vn divided by 1 plus GMRS, right? Okay, so now we got this equation. Why do we need this equation? We need this equation in here because we want to calculate the output by Vn, right? Let's go on the next page. So, okay, let's make it. So my V output, that's it. So my V output is equivalent to Gm RD. Vs is now equal to Gm Rs Vn by 1 plus Gm Rs minus Vn. Okay, that means my V output by V input, taking V in here as a common, subtracting here as well GMRS minus 1 minus GMRS divided by 1 plus GMRS. This and this will go. That means my V output by V input will be minus GM RD divided by 1 plus GM RS, right? This is your game. Any questions till now? Okay, now the question says this is an approximate gain. So we can assume here that for GM R is greater than 1, we can say that V output by V input is nearly equivalent to minus GMRD divided by GMRD, GMRS. This and this will go. That means it's equivalent to minus RD by RS, right? And given in the question, this is equivalent to minus 5. So my RD is equivalent to 5 RS. This is our third condition, right? Now we have three conditions at our disposal. Now we'll see how we can use these conditions. Okay. Now next thing is, next we use these three conditions. Now next is the device can go to the largest possible range. Okay. Since it's given that the device can go to the, we have to impose a condition, and then we'll be able to solve the whole question, right? For example, if I have V output here, this is some V output, and this is VDD, and this is some voltage, let's say VX, okay, and this is your ground. So if your V output goes above this voltage, it cannot go. If it goes above this voltage, your device turns off, right? And similarly, if it goes below this voltage, let's call it as V saturation voltage minimum. Sorry, not this. This is V saturation voltage. Let's say this is VD, this is VS, so that means this is VDS. So for a VS condition, this VDS should be such that it should not go below this value. That means it will not remain in. This is VDS we are talking about, right? For example, this is VDS. Okay. So let's say this is minimum VDS. Similarly, we are given that we have to find the largest swing. What is the largest swing possible? Now, in terms of current, okay. Now, let's say this is your DC current. This is DC, okay. On top of it, you have always your ID is ID plus ID, right? Now you are varying this current, right? So this current can go above this as well as below this now. Okay. So uh, since this has both the directions, this ID, what is the minimum value this can go to? ID minus ID. And if ID is equivalent to ID, this can go to 0, right? And maximum ID, and if it is equivalent to ID as well, it can go to twice ID. So let's assume that this device is at this condition such that there is a large swing possible, because only in this case, if your device is kept at such a way that this is a DC, then your ID can have a swing such that it has ID above, ID below, right? So the maximum ID is 2 times ID. Sorry, this is small ID. I have to write here I capital D. So is maximum current that is flowing through a device can be 2 times ID. Now at this condition, at this maximum condition, we have to check if your device is in saturation, right? Because if you see from the circuit, if you see from the circuit here, we have RS here and we have MOSFET here. If low current flows, right? If ID is low, That means this is VDD, this is your VS. That means there will be a higher potential here. VS will be large, right? Similarly, if high current flows, VS will be less, right? So we have to impose this condition using this as well to check that your device should always be in the saturation, right? So that condition is you have to check at this condition. So that means if I use this formulation, we have K times VSG minus VT whole square. Now we have to use ID, that is 2 times ID should be equal to VSG minus VT whole square. So that will give us a condition for VSG minus VT equivalent to 2ID by K. That is under root 2 times under root ID by K. We calculated this earlier, ID by K, that is 1.414 into 0.179. That is 0.25. At this condition, we need our device to be in saturation. So I can write as my VS or sorry, my VSD should be equal to VSG minus VT of 0.253 volt. And this will impose a condition on RS. You can see here in the circuit there is your RS resistance. Now we have to calculate this RS resistance such that at this maximum current the device is still in the saturation. So we'll write a KVL. So I have here this VDD, I have here this RS and RD. This is grounded, this is S, this is D. So what I can write is VDD minus ID. Now this ID is a simple current, normal current. No, so not normal. This I am 2 times ID at this condition, at this maximum condition, we need our device to be in saturation as well. ID RS is equivalent to this potential, right? VS, and VS is equivalent to VSD plus VD, right? Now VDD minus IDRS is equivalent to VSD plus VD. VD is simply IDRD. Okay, so that means my VDD is IDRS plus RD equal to VSD. Now from one of the calculations, what we did is we calculated here. What's that? Okay, here RD is 5 times RS, right? So I can write VDD minus ID is here 2 times ID, and this is 5 times RS is equivalent to VSD. Okay, so VDD is 5 and this is ID is 124 microampere. This is 5, this is RS, and VSD we calculated it should be at this point is 0.23 volt. So this will be the answer for RS divided by 2 into 124 micro into 5, and this is the condition for RS such that no matter the what quiescent point you select for this MOSFET, because this is the maximum condition for the current that will be flowing through the device, your device will remain in the saturation, right? So RS comes out to be, if you can calculate it, okay, this is equivalent to 3.2 kilo ohms approximately. Okay, so this was one value. Another thing we had to calculate is we had to calculate R1, R2, RS, and RD. And now we have RS in our hand, so we can calculate RD as well. That is 5 times RS. Okay, so now if this is done, and we had also calculated one more thing, that was the first equation. Here, no, this is R1 plus R2. Yes, here, number 2. VSG minus VT is 0.179 volt. Now we will use this. Now we will use this. VSG minus VT is 0.179 volt. That means Vs minus Vg minus Vt. Vt is zero point 0.5 is equal to 0.179. Vs we calculated. Do we have Vs in our hand? We can calculate now, right? This is VDD minus ID Rs is equal to Vs, right? So that means this is 124 microampere multiplied by 3.2 kilo ohm is equal to Vs. When you calculate it, just going to do this 0.124 milli multiplied by 3.2. It comes out to be 4.6032 volt. Okay, this is 4.6032 and this is Vg here is equivalent to 0.179 plus zero point 0.5, which is 0.679. So Vg will be equivalent to 3.9242. This is Vg. Now if you know this is if this is R1, this is R2, this is your MOSFET. Okay. So what will be here Vg? If this is Vg, what will be Vg here using the voltage divider? It will be simple,
VDD into R2 upon R1 plus R2.
right? This will be R2 divided by R1 plus R2 into VDD, right? Simple voltage divider. And you know R1 plus R2, we calculated that in the first equation that was 10 mega ohm into 5 volt. Now Vg, you know, it is 3.924 volt. That means this will be Vg 3.9242 multiplied by 10 mega divided by 5 will give you R2, right? So basically, my R2 will be 3.9242 multiplied by 10 divided by 5. 7.848 mega ohm. And similarly, you can calculate R1 from this equation. R1 plus R2 is 10 mega ohm. Okay. So these are the 4 parts in this question. All right.
Sir,
Yes, yes.
can you explain what we did in the fourth condition, that swing one? I did not get that.
Okay. The fourth condition says the output can swing symmetrically. Symmetrically means if this is maximum in this direction, it should be maximum in this direction as well, right?
Yes.
Okay. So if we assume that your device is optimally biased at some point, okay, that we wrote it as ID. Here ID is 124 microampere, right? Just biased at this one. Okay. So what is the maximum your current can go at the output?
2 times ID.
Okay,
if
you
we
cannot.
consider small signal ID to be equal to the DC operating current.
Oh, okay, you cannot. Okay, in the maximum you cannot say as such. But what is the minimum you can go from this minimum side? If you go to ID, if your ID small signal current plus a DC equivalent current, no, sorry, if your small signal current goes to ID in the negative cycle, it will turn the device off, right?
Yes,
It cannot go above this ID. So your maximum swing, what is the maximum swing in your negative cycle then? That is ID, right?
yes,
Okay, your small signal can swing maximum to ID. And similarly in positive cycle, it has to go to ID only because we are talking about symmetrical, right? So in the positive direction as well, it can go maximum of capital
ID.
ID. So this is the condition, that is the maximum current that is flowing through a device can go to 2 times ID. Okay. So at this condition, you can see your VSD should be minimum equivalent to this volt to keep the device in saturation. Is it correct?
Yes,
Yes. Okay. So if 2ID is the maximum current that is flowing through the device and you want your device to be in saturation, so you have to impose a condition on RS. Okay. So maximum current, because this is simple. Let me just draw here in this box. This is my VDD. Okay. One second. This is my VDD. This is my RS. And let me just draw VS. Okay. And here VD. Now, if you go on increasing the current here, if current increases, what will happen to Vs,
VS will decrease.
right? Because whole drop will go across this resistor.
Yeah,
So, what is the maximum current that is flowing through here? 2ID, right? At 2ID,
yes,
you want Vs minus Vd sufficient such that it has to be equivalent to Vsg minus Vt. Okay, this is the maximum current flowing in a device. So that means you have to keep RS in such a way such that this Vs potential minus Vd potential is minimum, equivalent to minimum, its minimum value should be equivalent to Vsg minus Vt. Is it understood?
yes, sir,
Or
understood.
I can repeat
Thank you,
it
sir.
if you want. I can repeat.
No, sir, understood. Thank you.
Okay. 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 Anyone else has some question about it? Because this was the important part of this question to solve the whole question. If anyone else has some doubt, I can explain again. Okay. Anyone wants to? Anyone has any doubts how we calculated gain and all? Yes, please. Yes, sir. Go ahead. Your mic is muted. Uh, your mic is muted.
You are applied KCL at point S, node S.
Yes, yes. Here, yes.
Uh, Now, if you applied KCL at point, node S,
Hmm.
okay. mm,
What is the doubt, sir?
no, my doubt is how you applied it. I just want to know the in the
Okay.
equation you are derived
Okay,
at
okay.
point S,
O-
where the current is
Okay, let me just read off here. Here. This is,
is going
yeah.
downwards from the arrays.
Yeah, you can. Okay. So let me just draw something here. Okay, let's say this is a network here, R1, R2, R3. As long as you are following the same convention, it doesn't matter what is the current direction you take. Okay. Let's say if I take this resistor has current in this way, this has this way, this has this way. So what you need to do is you need to write the equations properly. Let's say if I use this node as the KCL. So that means this is a zero potential. So current is coming inwards, current is going outwards. So current coming inwards has to be equivalent to current going outwards. Okay. So this will be zero minus, let's say this is the node Vx. So this will be 0 minus Vx by R1 is equivalent to Vx minus 0 by R, sorry, this is R3, R3, R1 plus Vx by R2. Now, this is one equation. Let me just write it now. What it will be equivalent to? This will be simply Vx by R3 plus Vx by R1 plus Vx by R2, right? Equivalent to 0. Now,
Yes, right.
what if I reverse the direction now? So how will you write your equation now? This will be simply, because all three are going outwards, this will be simply Vx by R3 plus Vx by R1, R2 plus Vx by R equal to 0. As long as you stick with the convention and you follow the KCL properly, it doesn't matter what is the direction you take. Similarly, in this direction, I took a current direction from node S to 0 and another current is from this node to the output node. So what I need to write is both are going outwards and there is no incoming current. So that will be 0 equal to Vs by Rs plus Gm Vs G. Now what if I had drawn the current in this direction? So I had to write Vs by Rs is equal to Gm Vs G. That's what KCL is, right? I hope you
Mm.
understood. Okay.
Mm.
Is it is it understood now?
Yeah, yeah.
Okay. So we can move on. If anyone has anything else, so before we can move on to next question.
Sir, generally when we use an NMOS device, the GMVGS current points downwards.
This
Yes.
is this is
But
PMOS.
okay, that was my doubt.
Oh yeah, this is PMOS.
Whether
So
for
that's a,
PMOS device. Okay,
hmm, that's why I have written VSG.
okay, got it.
Okay. So in the first slide I have shown here, arrow is pointing inwards. That means this is a PMOS. And for NMOS, arrow is always pointing like this. You can just note down this for notation how to know whether it's a PMOS if it's not written. Okay. So this is it from this set. Mhm. Okay. Now, in the last question, we ignored channel length modulation. Now, in this question, the lambda is given to us as 0.05 torr. Okay. What is lambda? And I derived in the last section. Everyone remembers what is lambda and how we get this parameter. I had shown the derivation as well in the last session. If you have not seen it, you can check the same YouTube playlist. The video will be there. Okay, so it's given that we have to use the previous DC operating points, calculate the actual small signal gain of the earlier circuit. And here we have been given GMB as well, which is 1 by 5 of GM. Okay, so I gave you the idea how to calculate small signal gain in the previous question. What is the difference here in this question?
ID will change.
Mhm. Okay, so let me just first draw simple DC circuit. Okay, this is your DC circuit. Now you have to calculate gain and you have to consider channel length modulation as well. So let me just draw the AC equivalent and you can suggest me how what steps we can take. Okay, this will be my V input. This will be R1 parallel R2, right? Because VDD will be grounded, will be grounded. This is my VG. This is RS. This is GMVSG. Second, need space. This is RS. This is no, this should be VS, G, and we have another current source that is GMB. Okay, that is like this. And we have RDS here, and we have RD here. This is VR. Is it understood how I draw this circuit? Any confusion till now?
No, sir.
Okay. So what is this RDS? It is basically simply dID by dVDS. Not showing the derivation here. You can check the previous session. How do we calculate RDS? Simply. Anyone knows the formula?
1 by lambda ID.
Okay. This is 1 by lambda ID. And this is approximated relationship, right? So your ID is, which ID you have to use?
Uh, 124 microampere.
Right. Because we are given use the DC operating point that you may have already calculated. Okay, that is from the previous question. What is the operating point, by the way? This is the most often used term, operating point in the circuits. What is the operating point?
VDS comma ID.
Yes. So operating point is basically what are the DC conditions at which your circuit is biased. Okay. What is the current flowing, DC current flowing through the circuit? What are the potentials? Okay. These are called as operating points. So this is my operating point ID 124 microampere. You can use this here to calculate RDS. Let me just calculate it. Divided by 0.05 divided by 124. Okay, this is 0.16 mega ohm. Okay, this comes out to be 0.16 mega ohm. Is it correct? Yes. Okay, so this is the value for RDS we have to use here as this value. Now there are multiple ways to calculate gain. Okay, I will show. I will try to show two. I will show first one, then I will give an idea of what is the another way. That is the simplest. That is the one of the approach that we used in the earlier question, right? Okay, to give an idea, we didn't actually we tried to use that as well. That is the source called that's called as the source degeneration. Here, like we did in this analysis, we have RS here as well. So you can see GM reduction by 1 plus GM RS. This is called as actually the source degeneration. So we need to do this kind of analysis here as well. So one method is calculate total output resistance. Okay. What is the gain actually? You give the input. Okay, then you see what is the intrinsic transconductance. Okay, and you multiply them, you get the gain of this, right? For a simpler circuit, if this is V in, this is grounded, let me drawing it for NMOS, VGS, this is RD. Can you tell me the gain directly? What will be the gain for the circuit?
GMR minus GMRD.
So my V output will be GMRD V in, right?
Yes.
Gain will be minus GMRD. So basically, gain is your GM, that is transconductance, multiplied by output resistance. Correct? Now,
Yes, sir.
what is this transconductance? This is I out by dV in.
VGS.
Yeah, that is V in. VGS, V in, you can say both because here V in is VGS. Okay, so this is D output by dV input at V output equal to 0. Actually, this is the condition for uh, GM. Okay, now the method is calculate total R total output resistance, that is R out, and calculate transconductance. V output, you have to keep V output equal to 0. Okay. Do you know how to calculate output resistance in any circuit? If you want to calculate output resistance, sorry,
We can short the independent DC, independent voltage sources and open the current sources.
and then what is the step? What is the next step?
We look in from the output and we apply the voltage at the output and check what amount of current is flowing through each resistor and then.
Yeah, absolutely. For example, this is a resistor R. Okay, I don't know what is the resistance. I calculate voltmeter. Okay, I connect it with a voltmeter. I connect it with a voltmeter, and I know what is the, let's say I know the and I have the ampere ammeter as well. I know what is the current is drawing. It's denoted as Vx, Ix, and I know the voltage, that is Vx. Now my resistance will be simply Vx by Ix. That is the method, right? So let me just show it for the small signal circuit. V in, let's say this is Rs. Yeah. This is VM VGS. This is RD. So how you calculate a resistance in this circuit? What you do is, this is output, right? Short the output. Okay. Let's keep it shorted, or we remove the section for now. Okay, and connect a voltage source. That is the potential of Vx. Okay, so current is flowing. That's equivalent to Ix, and let's say there is a resistance here RDS as well. Okay, so this node is at a potential of Vx. So how can you calculate R out? R out, for R out, you have to know Vx by Ix, right? So what will be our first step? KCL at this node. Let's say current is flowing in this direction, current is flowing in this direction. So my Ix, that is incoming, is equal to outgoing currents, that is VGS plus Potential here is Vx, potential here is Vs, right? That is Vx minus Vs by Rds. Okay, so this will be Gm minus Vs because uh, we have to ground it as well to calculate the resistance. So this will be minus Gm Vs plus Vx by Rds minus Vs by Rds. Okay, okay, so my Ix is now equivalent to minus Gm Vs plus Vx by Rds minus Vs by Rds. Now what is the variable here? That is Vs. Okay. Now Vs is the total current that is coming here. That's Ix. So total current coming to this node. That means it has to go output. It has to go out from this node as well, right? So this current will be equal to Ix. Is it correct? So my Vs will be simply equal to IXRS, right? So my Ix is Gm IXRS plus IXRS by RDS minus IXRS. So this has to be something else. This has to be Vx and this is RDS. So this will be Ix plus GMIX RS plus IX RS RDS is equivalent to Vx by RDS. Taking Ix as a common, so what I will get is 1 plus GMRS plus RS by RDS is equivalent to Vx by RDS. Now what is R out? It's simply Vx by Rx. That I need to just divide Rx. I need to transfer it here and this will go here. So Vx by Ix will give me R out. And that will be simply equivalent to Rds multiplied by plus GMRS plus Rs Rds. So to know that you have correctly derived this R out, check the units. One is unitless, GMRS is unitless, right? RS by RDS is unitless, and RDS is a unit of ohm. So R out has the units of ohm. So this is correct. So this is how you can calculate resistance of any circuit. Okay. So the same thing we'll use for this question as well. And it's a little bit of complex circuit. So let's connect source here, Vx, Ix. Okay. Just like that. So it's right. Okay. Now this Ix. This Ix, this is RDS here. Okay. This is your Vx. This is Vs. Again, this Ix will be equivalent to Vx minus Vs by Rds plus these. These are okay. So these are coming towards the node, so I have to write it this way. Ix Ix plus Gm Vsg plus GmB Vsb is equivalent to Vx minus Vs by Rds. Is it correct? Can you please check? Ix is coming inwards. These two currents are coming inwards, and this I have denoted as like this. So it's correct, right?
Yes, sir.
Okay. So this will be Ix plus Gm Vs because this term will be equivalent to 0. 1 second. This will be Gm Vs plus GmV. This is simply again Vs is equal to Vx by Rds minus Vs by Rds. Right? Second, is it 14? Here is the circuit. So, okay, so this is the equation. Just note it as Ix is equal to Vx by Rds minus Vs by Rds. Sorry, Rds is wrong. So this will be 1 by Rds minus Gm minus GmB. Okay. Now I need to calculate Vs. So how we calculate Vs? Again, KCL at node S. Okay, let me just check the circuit. KCL at node S. Let's treat it as a current going in this direction. These are going in this direction. And I have this current as well. That is Vs minus Vx by Rds. So I can directly write here Vs by Rs are going outwards plus Gm Vsg plus Gm B Vsd plus Vs minus Vx by Rds equivalent to 0. Okay, so this will be Vs by Rs plus Gm Vs plus Gmb Vs plus Vs by Rds is equal to Vx by Rds. Okay, so taking Vs in terms of Vx because that's what we need here. We need a Vs in terms of Vx. So Vs is 1 by Rs plus 1 by Rds plus Gm plus Gmb is equal to Vx by Rds. Let me just denote it as alpha. Okay, so my Vs is Vx by alpha Rds. Alright, so now from the previous part, we have calculated Ix. So my Ix will be Vx by Rds minus Vs, that is alpha Rds. That is denoted as beta. So this will be multiplied by beta. So that means Vx will mean Vx by Rds will take as a common. So that is 1 minus beta by alpha. Okay. So we have Ix is equal to this. I can write it as Vx by alpha ds alpha minus beta. So Vx by pi x, that is your R arm, is equivalent to Vx by x, that's alpha RDS by alpha minus beta. Okay, now we substitute the values. Substitute these alpha and beta. You know now alpha, you know now beta. Beta is here. You will get R out. Okay, let me just write it. Alpha is 1 by Rs plus 1 by Rds plus Gm plus Gb Rds and alpha minus beta. Alpha has these four terms, and you see that from beta, beta has Gm and Gb minus and plus. One second, there is some mistake. This should cancel out. Let me just check the KCL again. This is image. It's just image. Here's the first one. One second. Ix should be equivalent to okay, we can check this. Okay, just solve the equation. You'll get it as alpha minus beta 1 by Rs plus 1 by Rds plus Gm plus Gmb minus beta. Beta is um, second. X is Vx plus k Vx by Rds minus Vs times beta. Right. So this is Vx. This is alpha alpha minus beta. This is alpha minus beta. Okay. Minus we have to minus 1 by RDS. 1 by RDS minus GM minus GMB. You need to check it once the this is the signs are correct or not. Okay, this is I can write it as RS RDS. This will be RDS plus RS plus GM plus GMB times RDS whole divided by RDS and RDS will go This will be 1 by RS plus 2 times GM plus GMB. Okay, this is your R out, but this is not your total R out, right? Because total R out is this value parallel to RD, right? We had neglected RD in our analysis. So total R out is here. This total R out is this we calculated as R out, and it is in parallel to RD, right? Do one thing. Mm, Try to solve this at the end as well. This is small signal circuit analysis. Calculate R out using the method I have shown. And if there is some discrepancy, we can just let me know in the next section. Next session. Okay, so this is one. Have to calculate R out, and next is we have to calculate effective GM, right? Since there is a source resistance, drain resistance, so GM will change. So again, if we just here directly, I will use this the input here. This is the input that has to be equivalent to zero. Sorry, not zero. This time it's not zero. This is RS. This is J and VSG. This is GMBVS B. This is RDS. This is your RD. This is the out. Okay. And this is your I out, right? So I out is from this one. So can I write I out is equivalent to GM VSB plus GM VSG plus what will be the next one? VS, right? This is VS, this is VS, this is V out. So it has to be VS minus V out by, so this is I output here. VS minus V out by RDS. But we know when you calculate GM, this is that V output is equal to 0. So I output will be GM times Vs because VB is 0 plus GM times Vs minus GM times this is VB, GM times Vn plus Vs by RDS. Now the goal is to calculate I output by Vn, right? Okay. Now I output is GMB plus GM Vs minus Vs by RDS. Sorry, I can write it in brackets as well. Minus GMV in, right? Now next is I have to calculate VS. Again KCL at node S. So what will be the KCL at node S? Here at this node. Let's write once here. That will be VS by
VS
RS.
by RS plus GMBSG plus GMVSB plus VS minus V out by RDS.
Hmm. VS minus V out is 0, so it will be simply VS by RDS equal to 0, right? Correct?
So for calculating GM, we keep V out as zero.
Yeah, yeah.
That's one. Okay, it's the condition.
Yes. So this is called as a short circuit transconductance. Okay, so you need to calculate I output by RV in, right? That will be output equal to zero. So at this node, we calculated V KCL as Vs by Rs plus GM VSG plus GMB VSB plus Vs by Rs equivalent to zero. So again, this will be Vs. I will skip the two steps. This will be Rs plus RDS. Here, this will be Vs minus Vg. So this will have one term of GM, and similarly, this has one term of GMV and minus GM. V input equal to zero. Okay. From this equation, I can write Vs in terms of V in. Let's know denote it as alpha. 1 second. So this will be alpha times Vs is equal to GM V in. So my Vs is Gm by alpha V in, right? So now from the previous part, I need to replace Vs by this term. So my ion,
So
yes.
where did we get that minus GMV in term from?
Okay, this is from this term here, GmVSG. GmVSG is GmVs minus Vg, right? And Vg,
Okay, separated.
yeah, Vg is V in, right? So this is GmVs minus GmV in, right?
Yeah, got it.
Okay, so my the output is now Gm by alpha V in multiply by this term. Let's call it as beta. Let's call it as beta. Let's call it as beta minus GMV in, right? So I output is GMV in. I will take common. This is beta by alpha minus 1. So this will be GMV in beta minus alpha by alpha. So I output by V input is equivalent to GM. Let's now see what is beta. Beta is GMB plus GM plus 1 by RDS, and alpha is 1 by RS or 1 by RDS, GM plus GD. You can see three common terms, and it has to be subtracted. So what is left is minus R 1 by RS, right? Divided by alpha. Alpha is 1 by RS plus 1 by RDS plus GM plus GMB. Okay, this is my output by V input minus GM. Denominator will multiply through by RS. I will get 1 plus RS by RDS plus GM plus GMB times RS. Now, if I multiply it forward by VDS, RDS in denominator, we will get minus GM RDS divided by 1 RDS plus RS plus GM plus GMB RS. Now, know that for a transistor, maximum gain is GM RDS. That is the intrinsic gain, okay? So this is the maximum possible gain you can get from the transistor. You can see here from if there are channel non-idealities like we have source degeneration, we have intrinsic resistance RDS. and we have G and GMB, so the gain reduces, right? So this is your effective G effective. Now your small signal gain will be G effective multiplied by R effective. Okay, you now have G effective and calculate R effect, R out effect total as well. Just once try to do a calculation for R out as well, uh, because I think there should have been these terms should have been cancelled. There should have been positive signs here, but during the calculation maybe I have done some mistake. So you can try this, uh, and you can.
Sir, that GM and GMB in the denominator are positive or negative?
From my calculations, I got negative, but I think it has to be positive.
Sir, I think you wrote positive before, I think.
This is R out. This is R out. In GM, we got the positive, but
Yeah, yeah, I know. I'm talking about arrows only.
R out, I think I have done some mistake. You can check this mistake. You will have this PPT. You can just notify me in the next session. Okay.
Okay, sir.
Okay. This was one way in which you can calculate your G effective. This is a very effective method. Another is if you can directly, if you have good honed on your analysis. Okay, I will just give an idea. That is the method we directly use for simpler circuits, right? You don't need to do this separate analysis. What you can do is your V output is simply equal to I output times RD, right?
Yes, sir.
So what you can do is you can directly do the analysis. This is your VS. Your I output is like this. It will be GM VSG plus GMB VSB plus VS minus V output by RDS. Okay, so your I output is GMVS plus GMBVS. I'm skipping the steps, so this will be VS minus GMV in plus VS by RDS minus V output by RDS. So what is the next step? To calculate VS, right? KCL at node S. So if I do the KCL here, let's denote it as a current here going this way. So this will be Vs by Rs, current going away again, Gm Vsg plus Gmb Vsb plus Gm, sorry, not Gm, plus Vs minus V output by Rds equivalent to 0. So my Vs, I'm skipping the steps again, plus Gm plus Gmb plus Vs, sorry, this is to be 1 by RDS is equal to V output by RDS. Correct? Let's denote it as alpha. So the Vs is alpha times, not alpha times, 1 by alpha times. V output by alpha times RDS. Okay? So I will just substitute it here. I output is equivalent to GM plus GMB plus this is one by RDS as well. VS is the output by alpha RDS minus GM V in plus Vs again, that is V output by alpha RDS minus V output by RDS. So can you see why we are heading? We know the output is I output times RD. I can write I output in terms of V output as well. So this will be V output by RD. Transfer these to the left hand side. This will be V output by alpha RDS plus V output by RDS. Okay. One second. Okay. On the left hand side, it will be one second. This is okay. Hmm. So this will be V output 1 by RD minus 1 by alpha RDS plus 1 by RDS minus minus GM plus GMB minus RDS. Minus times GM plus GMB plus 1 by RDS multiplied by 1 by alpha RDS. How many terms is V out? 1, 2, 3, 4. So I need 4 terms. 1, 2, 3, and this one is 4. And it is equivalent to minus times GMV. Now we need to find a gain. So my V output by V input, if I just note down this as beta, so it will be minus GM by this beta term. And this in this beta term, you will see there are a lot of terms. So you have to just use the manipulation. And I think this one is the very simpler method than the previous one. Any doubts in this method? Anyone? We just directly did the analysis. The output is simply I output. Here the current flowing is I output multiplied by RD. Then we follow the simple KCL at this node and at this node to calculate the dependency. And we got because the goal was to calculate the output by V input, right? So that's what we did here. So we put the values and you will see that this alpha term, alpha 1 by S, and this has some common terms here. You can just check the manipulation and you can come up with the answer. And try to get the R out, correct R out for the previous questions and then match the two. And if there is some difference, and you can come up with in the next session. I guess uh, I guess we are done for today. We can continue this topic, calculating these gains, R out, R in the next session. If anyone has any questions, we can just take up here, and then we will start. So, okay.
Sir, what is the approach behind solving these MOSFET amplifier questions? Like, where should we start from?
In the MOSFET amplifier questions, always start from calculating first the DC conditions. Your DC conditions should be correct. Once you are done with DC conditions, then you can go to the gain and all. So, what is the question exactly? What type of questions do you have?
Uh, no, I mean, I haven't started solving questions because I joined the course late, so I'm still completing the previous week's lectures.
Mm-hmm.
So I'm yet to watch week one, two, three lectures, these
Okay.
problem solving sessions.
Okay. Week one was on diodes, and then you will see the other questions were on MOSFETs. While we just did those very like, for example, how you bias the device. Like we have voltage divider, or you connect it directly the biases. And then we did small signal gain analysis with the simpler circuits. In this section, there were some complex circuits, but in the previous sessions, you will see there were simpler circuits. So, like we have to calculate the series resistance. What is the gain? Like I showed one example to calculate the gain of small circuit. So that type of questions. If you have understood most part of the questions in the session, then you will find the other sections very easy.
Yeah, I understood today's session.
Okay, that's good. Yes, sir, please. Your mic is muted. Your mic is muted.
So my point was, since this calculation involves a lot of parameters, can you be able to reduce it so that it become easy to memorize, or can we shorten it so that values can we get closer to that value what is desired out of it? The problem. So point is, we are involving too many variables, and I mean we have to memorize it for that exam point of view, but there are too many complex equations are getting into.
No, you don't
Can you
need
able
to.
to shorten it so that exam point of view, where the time is a constraint, where
You,
we can get
okay,
a
okay. So actually, you don't need to memorize it. You just need to get an idea of the flow, how you do this question. For example, if I just if I now you know the process. If I will just give, for example, this analysis, let's say, if you in exam you have this type of question. Let's say you have RS here, simple circuit. You don't need to memorize the equations, right? You have to
Hmm,
calculate the gain. What is the step you have to take? First, you need to calculate what is the VG here, because they have to
hmm,
calculate G and VGS. Calculate first
hmm.
VG, calculate VG. Okay. Then the next step is what is your analysis at, let's say, let me call this as node X. Analysis
Hmm.
at node X, because this will give you output
Output, yeah, that's right.
output. Yeah. And then if there is a RS here, you need to construct VS as well, right? Because this
Hmm,
won't be zero. If there is no RS, then VS is zero. You don't need to consider KCL at this node. Okay?
hmm.
You don't need to do that. You just need to do the steps. First, you
Okay.
calculate the V input here. What is the V
Hmm,
input here? What is the
hmm,
V output? Then you just
hmm.
do the analysis, these steps, you will get the answers. One more thing, if you want to get the approximate answers, for example, in equation somewhere you got, let's say like this, 1 plus GMRS. You can assume somewhere that this GMRS is greater than 1. You can just simplify it to RD by RS. For example, here, let's say uh, this is 1 plus GM plus GMB RS. If I do a small bit of analysis, I can write it as 1 plus GM, not 1 plus RS plus GM plus GMB RS plus, or I can just simply neglect this term because RDS is usually very large, of the order of n is equal to 6, I can consider this as 0, right? You don't need to consider 0 here in this question, but you can consider it as 0. These are the simple approximations, like I can approximate this term as greater than RS or greater than 1 to nullify some terms. You can do such kind of approximations to solve your questions, but that easier part is you just follow the steps, you will get the answers. Okay.
Another point, sir, I want to make is, since these values are getting so closer to each other, the approximation, band is very thinner.
Now, what
It gets
values?
it gets at time overlap. May not be overlap, but then got very close. Then very difficult to choose between the two answers. When you have a four answers given, and
Mm-hmm.
then you want to compare. We have to select the right one, which is most closer to the value, which
Okay.
is
Oh,
at times become very very precarious and very closer. What I mean to say is little difficult.
to get the exact answer, that is will be the 100% surety. The answer is this, you have to avoid the approximations. That is the
Hmm.
only way. You need to
Yeah.
avoid the approximation. Unless it's
Yes.
given, unless it is given, that will be accommodated option. But if it's not given, if the answers are close, because most of the time the options are not that close. You can, for example, in this part, this R 1 by RDS, it will be nearly equal to 0 because
Hmm.
RDS is of the order of n is for 6. So you can use this approximation here. But if the options are closed, then you need to do the full analysis. And I think once you do these kind of circuits 3 to 4 times, you will find it very easy. You can follow a book like Behzad Razavi. Razavi is one of the book for this circuit solving. You can follow that book. Hmm. You will see a
These
lot
are
of
for
analysis.
problem solving.
Yeah, you will get for the basic understanding as well as the questions from the intuitive point of view. You will get a lot of intuition from that book. You can use that book to clear your understanding. That's a very good book. Mm,
Okay.
if
Okay.
you
Thank
can,
you.
okay. Thank you so much for joining.
Thank
Let's
you,
meet.
sir.
Let's meet next week.
Yes, sir.
Okay. Bye.
Okay. Thank you. Have a nice day. Thank you.
You too.